All right, welcome to the last section of new notes for Chapter 8 in AP Calculus, Taylor and Maclaurin series. So we have a theorem that says if a function f has a power series representation or a power series expansion at a, that is, f of x can be written as the series n goes from 0 to infinity of c sub n times x minus a to the power of n, where the absolute value of x minus a is less than r. Then its coefficients are given by the formula c of n is equal to the nth derivative of f at a over n factorial. So this notation means the nth derivative of f. If we go back to our original summation and plug that in for c sub n, then we get f of x is equal to the sum n goes from 0 to infinity of the nth derivative of f evaluated at a divided by n factorial, all times the quantity x minus a to the power of n. That function is called the Taylor series of a function of f at a. Sometimes it's said about a or centered at a. If we let a equal 0, then we would get the f of x is equal to the sum n goes from 0 to infinity of the nth derivative of f at 0 over n factorial times x to the power of n. This is then called a Maclaurin series. So a Taylor series and a Maclaurin series are exactly the same thing, except a Maclaurin series is centered at 0, where a Taylor series could be centered at any value. Find the Maclaurin series for the function f of x is equal to e to the x and its radius of convergence. So here we're talking about a Maclaurin series. So the x value that we're looking at, a, is going to be 0. We need to find some values of the function and its derivatives. We know if I plug 0 in for x in the original function, I get e to the 0 or 1. The first derivative at 0 would be e to the 0 or 1. The second derivative at 0 is e to the 0 or 1, and so on. So the terms in my series would be 1 plus 1 over 1 factorial times x to the first plus 1 over 2 factorial x squared plus 1 over 3 factorial times x cubed, and so on. In general, we can write that power series as a series n goes from 0 to infinity of x to the n over n factorial. So this first term can be thought of 1 over 0 factorial, and 0 factorial is indeed 1. Finding the radius of convergence, we go back to the ratio test, and we're going to check to see the values where x to the n plus 1 over n plus 1 factorial times n factorial over x to the n are less than 1. We have some factors that cancel out. X to the n and x to the n plus 1 cancel, leaving us with x to the first power in the numerator. N plus 1 factorial is the same as n plus 1 times n factorial. So the n factorials cancel, leaving us with n plus 1. So I have the absolute value of x over n plus 1 has to be less than 1. And I forgot, this is the limit as n approaches infinity. As n approaches infinity, my denominator goes to 0. My whole fraction goes to 0. Sorry, my whole fraction goes to 0. And 0 is always less than 1. So my radius of convergence is infinity. One relationship between Taylor series and other things is the fact that if we look at a partial sum of a Taylor series, we get a polynomial. And that polynomial is called a Taylor polynomial of f centered at a. So we'd have f of a plus f prime of a over 1 factorial times x minus a to the first plus f, the second derivative of f evaluated at a over 2 factorial times x minus a squared, and so on. Very often on the AP exam, you'll be asked to find the first 3 non-zero terms of a Taylor polynomial. And we'll actually do that in our homework as well. One fact that will be helpful and useful as we continue is the fact that the limit as n approaches infinity of x to the n over n factorial is always equal to 0 for every real number x. So we've already shown that e to the x can be written as a Maclaurin series. N goes from 0 to infinity of n x to the n over n factorial, and that's going to be true for all values of x. Therefore, e to the first power, when x is 1, would be 1 over n factorial as n goes from 0 to infinity, or 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on. So if we wanted to find a Taylor series for e to the x at a equals 2, in this case a equals 2, we would have to evaluate f at 2, f prime at 2, f double prime at 2, and so on. And our series would be e to the second over 0 factorial plus e to the second over 1 factorial times x minus 2 plus e to the second over 2 factorial times x minus 2 squared, and so on. In general, the series can be written as n goes from 0 to infinity. E to the second over n factorial x minus 2 to the power of n. For sine x, we're going to proceed similarly to the way we found e to the x. Again, it's a Maclaurin series, so a is 0. F of 0 would be sine at 0, not theta. Which is 0. F prime at 0, derivative of sine is cosine. Cosine at 0 is 1. F double prime at 0 is negative sine at 0, which is still 0. The third derivative of f at 0 is the opposite of cosine at 0, which is negative 1. And when we get to the fourth derivative, we're back to sine of 0, which is equal to 0, and the pattern repeats. So sine of x would have its first term 0 over 0 factorial x to the 0 plus 1 over 1 factorial x to the first plus 0 over 2 factorial x to the second minus 1 over 3 factorial x to the third plus 0 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth, and so on. If I eliminate all of the 0 terms, I would have x to the first over 1 factorial minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. To write this as a summation, we're still going from 0 to infinity. We have an alternating series, so we're going to take negative 1 to the n because our first term is positive. We only want odd powers, and we want the value of the exponent to be 1 when I plug in 0 for n. So we're going to take x to the 2n plus 1. We also want 1 factorial, so we're going to have 2n plus 1 factorial. And that is the series, the Maclaurin series for sine of x. This is one that you should memorize. E to the x is also one you should memorize for the AP exam. We will finish or continue on the next part